notes for AP Calculus on the topic of polar equations. And just a refresher on how polar coordinates work. You want to make sure you know how to convert back and forth between rectangular coordinates, which are our normal x, y coordinates, and polar coordinates, which instead of x and y, use r and theta, where r represents the distance from the origin to the point, and theta represents the angle right here. So remember where these conversions come from here. The two we'll use most often are these first two, x equals r cosine theta and y equals r sine theta. So if you take the cosine of angle theta, remember cosine using SOHCAHTOA is the adjacent over the hypotenuse. So that would be x over r. And then the way you can go from this to this form of this equation is just multiply both sides by r. And you can see the r's would cancel out, giving you x equals r cosine theta. That's where that conversion comes from. And then for sine, remember the sine of theta. Sine, remember, SOHCAHTOA is the opposite over the hypotenuse. So the opposite is y over the hypotenuse is r. And again, to get the simplified version of this conversion, we'll be using in this form. You multiply both sides by r. So the r's reduce out here, you get y equals r sine of theta. So these are the two we'll use the most often to go from polar coordinates to rectangular coordinates most often. And then the other ones you can see that you occasionally might need to use, but not as often, is x squared plus y squared equals r squared. You can see that just comes from the Pythagorean theorem since this forms a right triangle here. And then tangent of theta is y over x. You can see tangent is the opposite over the adjacent. So that would be the y coordinate over the x coordinate. And then the polar formulas for calculus, hopefully they look familiar because they're really the same formulas we use for parametric, except for t, we've got theta. So you can see it works in the same way. We've got dy d theta divided by dx d theta, because when you have dy d theta divided by a fraction, remember it's the same as multiplying by the reciprocal. So that's the same as d theta divided by dx. And then you can see the d thetas reduce out, giving you dy dx. And this dy dx still represents the slope of the tangent, just like it does for rectangular coordinates. It's just now you find it in a slightly different way because you have to find dy d theta and divide it by dx d theta. And the second derivative, this one, I haven't ever seen it on the AP test asked before, but they could ask you for the second derivative of a polar coordinate. And if they did, you would have to find the derivative of the first one. So you can see that would give you d squared y and then d theta times dx. But that's not what we want. We want the second derivative like this, d squared y dx squared. So then again, dividing by dx d theta, same as multiplying by the reciprocal, d theta over dx. And again, you can see the d thetas would reduce out there. And then really it's dx parentheses squared, but this is the shorter way it's written without the parentheses. So really the same idea as parametric, it's just theta instead of t. And the new formulas I'm going to look at that we can do with parametric ones are area. We did these with rectangular coordinates, a little different with polar coordinates. So it says the area enclosed between theta equals a and theta equals b is given by this. So let's see where this formula comes from. Polar coordinates are easiest to think about if you look at a circle. So if we draw a circle right here, and then here's about the center here. And we've got some angle theta, so I'm just going to pick some angle in here. So if we wanted to find the area of this segment of the circle right in here, then really we could start with, well, we know the area of a whole circle. Remember, this is R, the radius of the circle, just like it is for polar coordinates. So the area of the circle, would be pi r squared, pi times the radius squared. But we don't want the entire circle, we just want this part of it. So notice theta, it just depends on how big the angle is compared to, remember the whole circle would have an angle of 180 degrees, sorry, 360 degrees, all the way around, half the circle would be 180 degrees, 360 degrees, which is also the same as 2 pi in radians. So to figure out what fraction of the circle we have, we can just take our angle theta, and which is in radians, and then divide it by 2 pi. So if theta was 2 pi, it'd be the entire circle, 2 pi divided by 2 pi. But if it was pi, it'd be half the circle, and so on. And then when you multiply these together, notice the pi's cancel out. So the area of this would be 1/2 the radius squared times theta, however big that angle is. We do this area. However, with polar coordinates, sometimes we do get circles like this, but sometimes we can get other shapes besides just circles. So here's how this works here. With polar coordinates, and we draw another circle. The difference is, rather than having some large angle theta here, we're going to label this as d theta to represent a really small angle. In fact, what it actually represents is smaller than I can even draw, an infinitesimally small angle, d theta. Remember, d, kind of like delta means the change in theta. So if we have a really tiny angle here, and what we're going to do is take these little tiny angles here, the areas of these partial circles, and integrate all of those. So that's where the formula comes from. The 1/2, you can see it's pulled out as a constant. And then you have the integral from a to b. So a represents your starting angle, wherever these segments start at, these portions of the circle. And the upper limit b represents the stopping angle, wherever the polar curve stops at. So now they're representing the theta values. You can see it's d theta here. And so instead of theta right here, we've got d theta. And then we've got the radius is not a constant like it is in a circle. With polar coordinates, this radius is changing. So that's why it's a function of theta, and it's still squared. So you can see it comes directly from this formula. We're just adapting, integrating all these little tiny, you could say little parts of the circle there, adding them all up that have different radiuses to get the entire area enclosed by the polar curve. Similar to how we use rectangles for rectangular coordinates. Now, occasionally you might have an area you're trying to find that's between two polar graphs. And if you have two different ones instead of just one, and if they intersect at theta equals a and theta equals b, that's what you're going to need to figure out where they intersect at. Then, notice it's the same formula, except we have to take the area of the large one minus the area of the small one. So r sub 1 represents the inner radius. Sorry, the outer radius, I should say. That's the larger of the two. It's similar, it's going to look kind of similar to the disk method for rectangular coordinates, but that was for volume. This is for area. So, the outer radius. So whichever curve is farther from the origin on the interval, that is the outer radius, r sub 1. And then you subtract basically an area of the one that's closer to the origin. Okay? So inner radius is whichever curve is closer to the origin. So these are the primary new formulas we're going to be using today. Most often you just have the area of one polar curve for this first one, but occasionally you have to find the area between two polar curves. All right, let's look at some example problems now. The first one, we've got the graph of the polar curve r equals -1 minus cosine of theta. Sometimes it's written as just like this, r equals, sometimes it's functions r of theta. And it's shown below on interval 0 to 2 pi. That's probably the most common one you'll see for these polar graphs, but sometimes it's 0 to pi, sometimes you get other intervals besides that. So it creates this shape right here. And then part A says write but do not evaluate an integral expression. So we just have to set up the integral expression. We don't have to actually work it out. For the area enclosed by the polar curve in the fourth quadrant. So the fourth quadrant, remember, there's the first quadrant here, second quadrant, third quadrant, fourth quadrant. So it's talking about this little area right here we're trying to find. What is the area of that region? So we will need to figure out, well, which part of this graph gives us this fourth quadrant. Now, a common one, but not always what will give it to you. The fourth quadrant, normally think of the fourth quadrant between 3 pi over 2 right here and 2 pi, which sometimes it is. But it really depends on the curve if that's what it is or not. So the way you can tell is just substitute in some simple angles to see where the curve starts and where it stops and which direction it's going. So let's say we start with an easy angle like 0. Well, cosine of 0 is the x-coordinate, which is 1. At 0, so b, that would give you -2. So when you're graphing polar coordinates, you always start with the angle. That tells you what direction to go. And then this is giving you the radius, how far to go in that direction. So 0 is this direction, and on the unit circle, 0 is heading to the right. But if it was a positive 2, we would go 2 to the right, right over here. But a negative radius means you go the opposite direction. So that gives us this point on our graph right here. The 0 is this direction, you go the opposite, -2. So here you can kind of, to remind yourself, you can put, okay, this is theta equals 0. That's where the graph is starting at. Because notice we're going from 0 to 2 pi. So I'm going to just substitute, you can substitute whatever angles you want in this interval. Well, let's start, let's take another one that's fairly easy to evaluate quickly. So let's try the next one, pi over 2. So we find cosine of pi over 2. Well, cosine of pi over 2 is right here. Remember, cosine is the x-coordinate, which is 0. So that's -1 minus 0 gives you -1. So pi over 2 is the direction straight up, but again we have a negative radius, so it goes the opposite way. So that gives us this point on the polar graph right there. So that's theta equals pi over 2. So from this, what we can see is if we were asked to find the area in the third quadrant, right here, it would be from 0 to pi over 2. That's where it starts, that's where it stops, that would give us the area right there. And that's not what we're asked for the fourth quadrant. So let's keep going. So now we've got r equals -1 minus, let's try the next easy angle, pi, cosine of pi. So cosine of pi is over here, cosine is the x-coordinate, which is -1. So that's -1 minus -1. Notice those negatives cancel out, gives you -1 plus 1, which is 0. And whenever you have a radius of 0, that means it's right at the origin. So right here, this is, because you don't go anywhere in that direction. Pi is to the left, but the radius is 0, so we don't go anywhere. So here's theta equals pi. So now we actually have enough information to answer part A, because we can see this area, it starts at pi over 2 and stops at pi for our angles. So those would be our that's our starting angle, pi over 2, and our stopping angle, pi. So for the area, we're going to use this formula right here. If you got a 1/2 out in front, that's what's a little different. You don't have anything out in front when you're doing an area for rectangular coordinates. But for polar coordinates, it's always a 1/2 out in front. And then the integral from pi over 2 to pi, that's what we just figured out. And then it's always the radius squared. And here's our particular radius in this case. negative 1 minus cosine theta, so that's what goes in here. Negative 1 minus cosine of theta. And then don't forget, it always gets squared, and then times d theta. And this one said write but do not evaluate, so we can just leave it like that. And that, if we worked it out, either by hand or with a calculator, would give us the exact area of this little region right here in the fourth quadrant. All right, now let's take a look at same thing except for it asks for the second quadrant area. So the second quadrant, here's the first quadrant here, second quadrant. Now we're trying to find the area right in here. What is the area of that region right there? Okay, so we need to keep going because we can't quite yet see. It looks like it might start at 0, but it doesn't because it goes the opposite way. It could have started at 0 and gone this way, but it doesn't. So we have to figure out the starting and stopping angles there. So let's keep going here. The next one we've got, after pi, we can try 3 pi over 2. And cosine of 3 pi over 2, right down here is the x-coordinate, which is 0. So that's negative 1 minus 0 gives you negative 1. So 3 pi over 2 is heading down, but again we have a negative radius, so it goes the opposite way right here. So this gives you theta equals 3 pi over 2. So I think it's helpful, like I'm doing on the graph here, to label. You can visually see the radius, but to just label, not necessarily both coordinates unless you want to, but label the angle. Okay. And let's try one more, let's try 2 pi, that's where this interval stops at. So negative 1 minus cosine of 2 pi. So cosine of 2 pi, that's the same place right here as 0 cosine is 1. So that'd be negative 1 minus 1 gives you negative 2. So 2 pi, notice, is the exact same direction as 0 to the right. And notice we got the exact same value, negative 2. So this point starts at theta equals 0, and this is where our graph ends also, at 2 pi. So this is also corresponds to theta equals 2 pi. So now we can see, since we want the area of the second quadrant here, we can see it started at theta equals 3 pi over 2 and ended at theta equals 2 pi. So those will be our starting and stopping angles. So again, we just have to write but do not evaluate it. So it'd be 1/2 again out in front. Integral from the starting angle was 3 pi over 2. The stopping angle is 2 pi. And again, we have the radius squared, which is based on whatever the function is. Because the radius, you can see, is not, unlike a circle where it's a constant, it's changing as the graph goes. How far it is, radius is really how far it is from the origin. So here's our particular radius, negative 1 minus cosine theta, squared times d theta. Okay, so those were just writing but not evaluating. Oftentimes on the without calculator, that's what they'll have you do. In the with calculator, they'll usually have you evaluate. Okay, let's take a look at another one. This one says we've got the graph of a polar curve here, creates this shape right here. R theta, notice it's written in function notation this time, equals 1 plus 2 cosine of theta. And again, the interval, it's not always going to be this, but it happens to be 0 to 2 pi again. And again, we're just asked to write, but do not evaluate, an integral expression for the area of region R. So notice region R is just this little loop right here. That's what we're trying to find the area. What's the area of that little loop? So to find, kind of like we did here, it's a little trickier though on this one to find the starting and stopping angles. Here we can just figure out, in which quadrant we're trying to find the area. But on this one, notice this little loop, it starts and stops at the same place. And the key right there, we can't tell what the angle is. The one thing for sure we can tell is to hit this point, it can't go anywhere from the origin. So the radius has to equal 0. So let's use that to help us figure this out. If the radius has to equal 0, then say 0 equals 1 plus 2 cosine theta. And let's solve for theta to help us figure out the starting and stopping angles. Alright, so we first subtract the 1. then divide by 2. I'll just switch the sides around here. We'll get cosine of theta equals -1/2. And remember, cosine is the adjacent over the hypotenuse. So let's figure out what those angles are between 0 and 2 pi. So we want the adjacent to be -1. So in order for the adjacent to be negative, it has to be over in the second or third quadrant there. Draw our triangles in here. So the adjacent's -1, hypotenuse is 2, so it'll be that quadrant or that quadrant, and we just have to figure out what are these angles. Well, you can see this is the 30, 60, 90 triangle, so this is our 60-degree one. This side, if we need it, would be square root of 3, and here negative square root of 3. And 60 degrees is the same as pi over 3, so this would be pi, which is the same as 3 pi over 3 to get a common number. So you can see this is pi over 3 less than it. So this one is 2 pi over 3. And this is pi over 3 more than 3 pi over 3, so this is 4 pi over 3. So it looks like those are probably our starting and stopping angles here where the radius is 0. Just one thing we have to make sure of, the only thing we don't know yet is, does that interval 2 pi over 3 to 4 pi, does it give us the little loop or does it give us the big loop? So what you can tell real quick to see if it's the right loop or not is substitute an angle between these two. In this case, the easiest one between them is probably pi. So let's find r of pi, just to make sure it's giving us the little loop and not the big loop. So it would be 1 plus 2 cosine of pi, and 1 plus 2 cosine of pi again. Cosine is the x-coordinate of pi is -1. So that gives you 1 minus 2, which is -1. So pi is to the left, that direction, and -1 goes the opposite way. So this is where theta equals pi. So that's on the little loop, so that means we do have the right lower and upper limits. That it's going to give us this little loop and not the big loop. So then to write the expression for the area, be 1/2 integral, we figured out the lower limit, the starting angle is 2 pi over 3. The upper limit stopping angle is 4 pi over 3. That's where both of these, where the radius is 0, where the loop starts and stops. And then we have the radius squared. So 1 plus 2 cosine theta, that's our radius this time. Squared times d theta. Again, we just have to write but do not evaluate. And then part B deals with the same equation but asks for something different. It says find r prime of 5 pi over 6. And then we're asked to interpret this to say, what does it say about r, the radius, and what does it say about the curve? Okay. So, derivative rules apply just like with rectangular coordinates, same derivative rules. You just have theta as a variable instead of x or t. So, r prime of theta, first I have to find the derivative before we can substitute in 5 pi over 6. Derivative of a constant 1 is 0. And the derivative of cosine, let's use coefficients theta, is negative sign, so that becomes -2 sine theta. And then we can substitute in our specific angle 5 pi over 6. Will give us -2 times the sine of 5 pi over 6. So let's figure out what the sine of 5 pi over 6 is. over 6 a little bit less than pi, which is 6 pi over 6. So it'd be in the second quadrant. And then we have to find the sine right there. So 5 pi over 6, pi over 6, the reference angle here, same as 30 degrees, so the opposite is 1 of the 30 degrees. Hypotenuse is 2, so that would be 1/2. So r prime, 5 pi over 6, will equal -2 times, we just figured out sine of 5 over 6 is 1/2, which gives you the 2's cancel out, and you're just left with -1. Okay, so that's the first thing it asks us to find, figure out the value of it. R prime of 5 pi over 6 is -1. Now we've got to interpret this. What does this say about R? Well, remember the first derivative, this was R right here, always tells you whether the original function, based on whether it's positive, is increasing or decreasing. So that would mean, since we have a negative answer, the radius is decreasing. And if the radius is decreasing, what does that say about the curve? That means the curve itself, when the radius is decreasing, is moving closer to the origin. So that's the two different things it's asking you about on this problem when it says to address that. So you can say, first reference the time, at theta, of the angle I should say, theta equals 5 pi over 6. R is decreasing. That's what it says about R. And the curve is moving, you can either say closer to the origin or towards the origin. I'll just say closer to the origin. Or if it had been positive, or inverted, you could say that it would be R is increasing and the curve is moving further from the origin. Alright, let's take a look at another example here. Last one here, just a couple parts here. So it says the graph of the polar curve R equals 1 minus 2 sine theta. Notice this time, it's only graphed from 0 to pi, not 0 to 2 pi. And it says write expressions for x, dx d theta, and dy d theta in terms of theta. So whenever you're asked for something that involves x and y, we have to use those from the very first, the conversion, way to convert those. So remember x is equal to r times cosine theta. We'll use that to get dx d theta in there. And y equals r times the sine of theta. And then all we have to do is put in our, before we can find the derivative, put in our specific r. In this case, r is equal to 1 minus 2 sine theta.
Hang on a second.
Sorry about that. Just got a little interruption in my video there. So we need to convert these to be in terms of just x and theta to get dx d theta, and then for this one just y and theta. So we substitute our specific r right here. So here x would equal 1 minus 2 sine theta times cosine theta. And then you could take the derivative in this form if you want, using the product rule, or you could distribute it out first. It just depends on the problem. I think in this case it might be easier if we distribute out the cosine first, but either way is fine. So here we'll have x equals cosine theta times 1 is cosine theta, minus 2 sine theta times cosine theta. And now that we have x in terms of just theta, not in terms of r also, now we can find the derivative, dx d theta, that we're asked to find. So dx d theta would equal the derivative of cosine is, remember cosine starts with a c, so it would be negative sine. And then this one, if you treat the negative 2 along with the sine theta, you can use the product rule. You have to use the product rule on this one. So the derivative of the first one, is negative 2, derivative of sine is cosine, times the second one, cosine theta as it is. And then normally it'd be plus the first one as it is, but the first one is negative, so just leave it as it is. So you don't see that plus sign, negative 2 sine theta. Times the derivative of cosine is negative sine. And then we can just simplify it a little bit. You could leave it like this, but it'll be easier to work with if we simplify it when we get to part B. So dx d theta is negative sine theta, and then you can combine the cosine, so this would be minus 2 cosine theta squared. And combine the signs, the negatives also cancel out, so it'd be plus 2 sine theta squared. With the squared here or on the end. So now we have dx d theta. And then next we need dy d theta. So we have to again substitute in r, your specific radius, right there. So this would be y equals, the radius is 1 minus 2 sine theta times sine theta as it is. And again, it's probably easier, you could use the product rule here. In this case, it's probably even easier than the other one if we just distribute out the sine theta. So both of these. So we get y equals sine theta minus 2 times sine theta would give you sine theta squared. And now we can find dy d theta by finding the derivative. Derivative of sine is cosine. And then here we'll just use the chain rule, since we have a function inside. Bring down the 2 times the negative 2. Gives you negative 4 sine of theta. And then times the derivative of sine is cosine of theta. And then we can, that one really can't be simplified any further. So let's just leave it like that. So that's what part A asks for. And now that's going to help us when we get to part B. Because now it says write an equation in terms of x and y for the line tangent. So it's our normal tangent line problem, except with polar coordinates, when theta equals pi. So just like we normally do for the tangent line, there's 2 things we need, the point of tangency and the slope. So let's find the point of tangency first. we need the x and y coordinates, and that's where we can go right back to our expressions here before we found the derivative, because we know theta equals pi. So let's start with this one. Let's say x equals cosine of pi, right here, minus 2 sine of pi times the cosine of pi. Well, cosine of pi is -1. Sine of pi is 0, so that wipes out this entire term. So we just get -1. There's our x coordinate of our point of Tangency. And now let's find the y coordinate. Again, we use this one right before we found the derivative. So y equals sine of pi minus 2 times the sine of pi squared. But remember, we just figured out sine of pi is 0. So 0 wipes out both of these, so we just get 0 is our y coordinate. So now we know -1, 0. There's our point of tangency we use for the tangent line. And then for the slope, we just have to use the formula, remember, dy dx. In this case, specifically at the angle theta equals pi. Is equal to dy d theta, which we found here, divided by dx d theta, which we found right here. Just like we did for parametric points. The difference is, again, just like we did here, we're going to substitute in theta equals pi into each of these. Okay, so let's substitute in pi into dy d theta first. Right here, so that's going to be cosine of pi minus 4 sine of pi cosine of pi. And then on the denominator, the x d theta is right here. It'll be negative sine of pi. And then minus 2 cosine of pi squared. And then plus 2 sine of pi squared. So cosine of pi is -1. Sine of pi is 0. So again, that wipes out this entire term, so we just get -1 in the numerator. And notice we've got some sine of pi here. That's 0, that's 0, so those two terms are gone. And then cosine of pi is -1. But notice that gets squared, that makes it +1, times -2 is -2. So we just end up with -2 on the denominator. And then you can see we've got a negative divided by a negative. The negatives reduce out. So we get +1/2. So that's the slope of our tangent line. And then we write the tangent line the way we usually do. Now that we know the x and y coordinates and the slope, it'd be y minus 0, the y coordinate, so we don't have to write -0, that doesn't anything, equals the slope, 1/2, times x minus the x coordinate is -1, so that becomes x minus -1, the negatives cancel out, x plus 1. So there is our tangent line. Just takes a little more work with these polar coordinates than rectangular coordinates to get. And that concludes the notes for AP Calculus on the topic of polar equations without the calculator.